Welcome to Electrical Engineering with Excel. This is my 20th video about Excel and its amazing use in electrical engineering. If you have watched the previous videos in this playlist, you will find various methods of use. This video features some new tips and tricks you may find useful in your spreadsheets. Since I just finished up 2 videos on waveguides, I decided to use these tips and tricks in a spreadsheet for waveguide attenuation and power handling. Most of the workbook is already built, and I will preview some of its features first. Then I will introduce some new features. One is about a pesky issue with the chart's axis autoscaling, which we will create some Visual Basic for Applications code to remedy that. Another will be the creation of a gauge that will display the operating frequency range overlaid the usable frequency range. This will use a modified version of the 2D bar chart. Its axis bounds will also be adjusted with some Visual Basic code. I'll also make use of the new Excel filter spill array function. The standard waveguide sizes range from 0.32 GHz to 220 GHz. That's a span of nearly 22 decades. One feature the spreadsheet should have, in my opinion, is a plot of attenuation over frequency and see where your desired operating frequency band is within the range of the attenuation plot. A really cool feature of Excel's charts is that it automatically adjusts their minimum and maximum axis bounds to fit the data. Unfortunately, it has a mind of its own and doesn't fit the data properly at times. Let's look at an example. Here I created a scatter chart using these values. All the X values are near 100, but for some reason, Excel auto-scaled the minimum axis bound to 0. This means this much of the chart is empty and wasted. You could go change the minimum axis bound to 80 to better fit the data, but that would need to be done each time the frequency span changed. Ain't nobody got time for that. Here's a scatter chart of attenuation of WR90 aluminum waveguide. Its cutoff frequency is around 6.557 GHz. That cannot be plotted since the attenuation is infinite at the cutoff frequency. I started the plot frequency to be 0.1% higher than the cutoff frequency, which is 6.56 GHz. This seems to adequately show the waveguide and cutoff and still properly display the minimum attenuation at the high end of the frequency band. The auto-scaling of the x-axis gets set to 0. This much of the chart is empty and wasted. We're going to write some Visual Basic for Applications code to set the minimum axis bound to the value of a cell in the spreadsheet that calculates an appropriate number. The formula for that axis minimum rounds down the attenuation chart frequency by 9 digits, which yields the next integer value of gigahertz, which is 6. The plot now takes up most of the chart area now, going from 6 to 15 GHz. Here's the code used to set the minimum scale of the attenuation chart. It uses the built-in worksheet calculate subroutine. Using a with statement for the worksheet named waveguide loss and a chart property named attend chart, the property minimum scale of the category axis is set to a range name within the spreadsheet named attend chart fmin, the cell with the rounded down frequency number. I'll demonstrate some of the features of the spreadsheet. I'm not about to build a workbook from scratch here. I have demonstrated all the things I'm about to show you in earlier video versions. After an overview, I'll go over the newly added features in detail. Here's a page that contains the constants used in the workbook. C is the speed of light in meters per second. The resistivity of copper and aluminum is in nano-ohm meters. Also, the temperature coefficients, alpha for copper and aluminum. The maximum voltage breakdown in air at sea level is 30,000 volts per centimeter. I calculate the resistivity of copper and aluminum at max temperature using the standard formula. I use a if statement to return the resistivity of the aluminum at max temperature if the selected waveguide is aluminum. Otherwise, it returns copper. There's a waveguide datasheet here for the industry standard waveguide sizes. The lowest operational frequency is 0.32 gigahertz in this cell with the name of WGFMIN. The table was served to return the A and B wall dimensions of the selected waveguide. Going back to the waveguide loss sheet, let's look at the data validation for the inputs. The minimum operating frequency is a custom validation criteria with the AND function with two arguments. One is fmin is less than fmax, and the other is fmin is greater than or equal to the WGFmin times 1 billion, since the frequency numbers in the waveguide table are in gigahertz. Now for the maximum operating frequency, it's also an AND function with three arguments. Fmax is greater than or equal to fmin, fmax is less than or equal to 1.5 times fmin. This is the nominal maximum bandwidth of waveguide. And finally, fmax is less than or equal to WGFmax times 1 billion, which is 220 gigahertz. The waveguide selector is a drop-down list, which are the USA WR numbers column in the waveguide datasheet table. The selector right now has all the waveguide designators, but later we will limit it to the ones that can be used within the operating band. Next is a drop-down selector for the waveguide material, which has no cell reference, just the two material names separated by a comma. For the temperature, I allowed a decimal number between -30 and +100. The error alert is just a warning. A number outside that range could be entered after receiving the warning. The maximum input power in dBm has a similar criteria as the power level ranges from -50 to +100. Notice the number format. I added a custom number format that forces the display of a plus sign. It's +0, semicolon, -0, semicolon, and 0, which displays a plus sign if positive and a negative sign if negative, and 0 if 0. The broad wall size A uses the XLOOKUP function using the WGSelect as the lookup value. The WR size column is the lookup array, and the broad wall column is the return array. The narrow wall lookup is the same, but uses the narrow wall B as the return array. The cutoff frequency is calculated as C over 2A. The A dimension must be converted to meters, which is the convert function because the speed of light is in meters per second in the constants sheet. The cutoff wavelength is simply C over the cutoff frequency. The attenuation is calculated at the maximum and minimum frequency using the equation here. Notice how easy it is to interpret the formula when cell names are used. This cell calculates the attenuation chart axis minimum, which takes the cutoff frequency and rounds it down 9 digits, which is the integer gigahertz value just below the cutoff frequency, in this case 6 gigahertz. We will use VBA code later to dynamically adjust the chart axis bound. Here's the minimum frequency percent of cutoff, fmin over cutoff frequency, and it should be greater than 125%. And here's the maximum frequency percent of cutoff, fmax over cutoff frequency. It should be less than or equal to 189%. Here's the conditional formatting that turns the cell red if the value is out of range. Here's where the waveguide wavelength is calculated. First, the minimum operating frequency wavelength is calculated, which is C over fmin. Then the waveguide wavelength is calculated using this formula. Look how clear the cell formula looks with the Greek characters used in cell names. The minimum operating frequency is used because that yields the minimum ratio of lambda naught over lambda g. That way, the power handling doesn't get overrated. Here's the formula for power handling. The A and B dimensions must be converted to meters. The input power is converted to watts here. And finally, the percent of maximum input power to power handling is ratioed in percent. This is the plot for attenuation versus frequency. This sheet holds the data for that chart. You can't start the chart at the cutoff frequency because the attenuation is infinite. So with some experimentation, I determined the minimum frequency to start the plot would be 0.1% above cutoff frequency, or FC times 1.001. It shows a good amount of cutoff region and still shows a decent amount of the region in operation. Following frequencies are 1.01 times the cell above it. The dB per foot is calculated per the equation here. The attenuation chart title is linked to this cell. It's dynamic. It concatenates WG select with the WG material and the text waveguide attenuation. Here it is in the waveguide attenuation chart with the chart title linked to the cell E1 on the plot data sheet. Also, the orange and green dots show the attenuation at the minimum and maximum operating frequencies. Now let's work in the frequency axis on the attenuation chart. Select the x-axis, then right-click to access the Format Axis command. Set the display units to billions. This will display the frequency in gigahertz. The text box with the word billions can be changed to gigahertz. Set the major units to 1e to the 9th, and set the tick marks for the minor type as inside. Now let's apply the Visual Basic code. Make sure the file has been saved as a macro-enabled workbook with the extension XLSM. Press Alt 11 to access the Visual Basic editor. Under Microsoft Excel Objects, double-click on the Waveguide Loss sheet. Drop down the General box and select Worksheet. Then drop down the Declarations box and select Calculate. Then delete the Worksheet Selection Change subroutine and paste in the code. Now go back to the Waveguide Loss sheet and change the selected waveguide. Now the chart adjusts for the frequency axis minimum to the value in cell G10. Go select another waveguide WR number, and it changes the minimum to the appropriate integer gigahertz value just below cutoff. Also notice that I formatted the chart and legend with a shadow shape effect. I think that looks pretty. Next up, I'm going to make a bandwidth gauge that will show the operating frequency band along with the usable waveguide bandwidth. For the usable start frequency, it's 1.25 times the cutoff frequency. The usable stop frequency is 1.8 times the cutoff frequency minus the start frequency above. For the operating frequency, the start is Fmin and the stop is Fmax minus Fmin. I'll select the 4 cells, and from the Insert tab in the Charts group, select 2D bar chart. Delete the vertical axis, select the grid lines, and hit delete. Also delete the legend. Right-click on the top left bar and select the fill to no fill. Right-click on the bottom left bar and select the fill to no fill. I'm going to select the bottom bar and make its fill color a light green. I'll also select the top bar and make its fill color a light blue. Right-click on the X-axis and select Format Axis. For display units, select billions. For the number format, select General. Overwrite the billions text box with gigahertz. Make some tick marks. Set the major style to outside and the minor type to inside. From the Chart Design tab, select Add Chart Element and the axis titled Primary Horizontal and name it Frequency. I'll move the chart area a little closer to the axis title. Select any portion of the bar to format the data series. Then click Series Options. Set the gap width to 0. Select the chart title, and from the formula bar, enter equals, and then select the F3 cell, where I have already made a title text for the chart. Right-click on the X-axis and select Format Axis. For display units, select billions. For the number format, select General. Overwrite the billions text box with gigahertz. Make some tick marks. Set the major style to outside and the minor type to inside. From the Chart Design tab, select Add Chart Element and the axis titled Primary Horizontal and name it Frequency. I'll move the chart area a little closer to the axis title. Select any portion of the bar to format the data series. Then click Series Options. Set the gap width to 0. Select the chart title, and from the formula bar, enter equals, and then select the F3 cell, where I have already made a title text for the chart. I'll reduce the font size a bit, then reduce the height of the entire chart and plot area. I'll select the chart and use the name box to give it the name BW Chart. Right-click on the chart area and select Format Chart Area and select Border and scroll down to the bottom and select Rounded Corners. I don't know why, but I like rounded corners. I'll click on the chart title, and from the Format tab, select Shape Effects, then Shadow. I'll use this first outer shadow effect. Right-click and select Move Chart as an object in Waveguide Loss Sheet. I want to make the chart the same width as the attenuation chart, so right-click on the attenuation chart and select Format Chart Area. Then select the Size and Properties button on the right. Then select Size and copy the width. Then go to the same property for the bandwidth chart and paste in the width. Select both charts from the Shape Format tab, select Align and Left. Then position it just under the attenuation chart. The native legend for the chart will not show the relevant value, so I had to make my own legend using colored rectangles and text. I'll reduce the chart area height to make room for the legend. Notice the frequency axis starts at 0, so we need to include the Visual Basic code to make it start at the same frequency as the attenuation chart. I've copied the code. Press Alt F11 to get to the Visual Basic editor and paste it inside the Calculate subroutine above or below the code for the attenuation chart. The code is the same as for the attenuation chart, except that the axis that we're changing is the value axis instead of the category axis. Change to another waveguide size to see it work. Finally, I want to make the waveguide size drop-down selector have only the waveguide sizes that are within the operating band. I'll go to the waveguide datasheet and add a column called usable. And I'll use the AND function with fmin being greater than or equal to the start frequency times 1 billion, since the values in the chart are in gigahertz. And also fmax to be less than or equal to the stop frequency times 1 billion. This will return a Boolean true or false. If we were to turn on the filter function in this chart and filter the usable column for true only, the waveguide size dropdown would still contain all these values. We must use the filter spill function to accomplish this. Before we do this, let's review how to select a column of data in an Excel table. You simply hover over the header cell of the desired column near the top of the cell, and you will see a small black down arrow. Then click. Notice it does not select the header cell. I'll use that method in the filter spill array function. I'll find a spot to the right of the datasheet and enter the filter function. The first argument is the array. In this case, it will be the waveguide size designator. The next is the include argument, selecting the usable column and set it equal to true. The third argument is what to return if empty, which I will make the text none. Isn't that cool? Now I'll go back to the waveguide loss sheet and select the waveguide size select cell. From the data tab, select the data validation and select the top cell of the filter spill array. Notice the dropdown only has WR90. The trick to make the list source follow the dynamic filter spill array size is to put a pound sign after the reference to the top cell of the array. Now the dropdown has both WR90 and WR102. Thanks for watching. Please click the like, subscribe, and notification bell so you don't miss any upcoming content.